Hi, welcome back to Statics 1. Today we're going to be talking about the calculation of moment of inertia for composite areas. So let me write that down. We're talking about moment of inertia for composite areas. That's our goal today. So what do we mean by that? By composite areas, we're referring to areas that are essentially the combination of multiple simple areas for which we already know how to calculate the moment of inertia. So for example, actually let me start at the beginning of what is the moment of inertia. We'll talk about the moment of inertia, we'll review what we already looked at before, which is the moment of inertia for rectangles. And then we'll look at some examples of the actual calculation for what we're referring to as these composite areas. So the moment of inertia is defined Ix equals, and it's a double integral over y squared dy dx. This is formally, we've done it, you can do it for kind of irregular shapes. For the most part, we're going to be doing it, evaluating it, and particularly when we're talking about composite areas, we're going to be talking about areas that are basically the accumulation of multiple rectangles like this. So if we have B in this direction and H in this direction, we know that. And if we define our axis, remember, it's important to remember, whenever you see Ix, you always got to ask for what axis, because there's not one value of I, moment of inertia for this rectangle, for example. Depends whether you define the axis through the midpoint, through the centroid, through the base. You can define it basically wherever you want it to be. And the minimum moment of inertia value is always calculated for the axis basically going through the centroid of the rectangle. So in this case, if we do that, let's say, for example, here's this, and we're going to call this x prime and y prime. Okay, we're defining our axes, x prime and y prime, to go through the centroid of this rectangle. And of course, we know that the centroid would be halfway up the rectangle, basically h over 2 from the base, and then b over 2, b is their width, from the left edge. If that's the case, then Ix, and typically what we'll do is we'll put a bar over it, which means that that's the moment of inertia through the centroid, or through an axis. Let me try again. That's the moment of inertia for an axis that goes through the centroid of the rectangle, and that'll be equal to b h cubed over 12. And if we have any other axis, let's say we have an axis at some point down here, so I'm going to call this x prime prime, and we have the vertical axis y prime prime, by what we refer to as the parallel axis theorem or parallel axis rule. We know that Ix prime prime. All right, so Ix prime prime is simply going to be equal to this value, this Ix moment of inertia evaluated for an axis through the centroid, plus our area, which in this case will be b times h. Should I put it, I'll write it that way. I'll just write area in general. A is the area, which for a rectangle would be b times h. But don't forget, we can evaluate a moment of inertia for many other shapes. So this rule is essentially applicable for all those shapes. In this case, we know that A equals b times h. And that would be multiplied by d squared, where d is the vertical distance It's the vertical distance between our axes. That's our d value between this axis and where we're evaluating our moment of inertia, and the centroid, or the axis that passes through the centroid of the area of interest. All right, so this is all kind of review so far. The same thing's applicable in the y direction. So for example, we could define y equal to double integral over, in this case it's x squared dy dx. And we could evaluate the moment of inertia for a rectangle where the axis passes through the centroid as I prime, and I'll do it right here, I of y prime with an overstrike on it equal, in this case, because we're evaluating it in this direction as opposed to vertically, we're going to have b cubed h over 12. So that will be our moment of inertia for an axis, the y-axis passing through the centroid would be b cubed h over 12. All right, so what are we talking about so this is all kind of review. Hopefully it's not unfamiliar to you. A composite area can be any area that can be broken down into other simpler component units. So for example, we could have a I-beam. So we might want to evaluate the moment of inertia for this type of a cross-sectional area. You might have some other shape. And typically when we evaluate these moment of inertias, it's going to tell us something about the bending response of our beam. So this might be a cross-sectional area of a beam. You might wonder, how much is this going to bend? The higher the moment of inertia, the less bending that's occurring. Likewise, this would be, again, this might be some other shape. And so we can break these down into multiple rectangles for which we know the moment of inertia of each of them would be basically like this value here, h cubed over 12. So in this case, we break this down into 3 pieces, 1, 2, and 3. So it's like 3 rectangles. And it may not be obvious to you, but the moment of inertia for those 3 rectangles is actually the sum of the moment of inertia of the 3 rectangles. And why is that the case? This is a simple integral. Remember, integrals are like summations. What we're doing is we're breaking our area, like in this case, we have a simple rectangle, into real itty-bitty units. These are basically like dxy by dy high, infinitesimal in dimension. And we're multiplying those by y squared. So if we're doing it for this axis here, this would be our y squared value. And we do this over and over again over the entire area and add, basically integrals are like summations. So we're adding those all up over the entire area. So there's no reason to expect that if we had like this area and that we glued onto it something here on the side, and we now want the moment of inertia of the entire piece, which consists now of essentially like 2 rectangles. There's no reason to think you couldn't just calculate the moment of inertia of this value, of this area, add it to the moment of inertia of that value. All right, so going by that kind of logic and looking at this I-beam here, you might realize that the I value and it could be both in the y direction or in the x direction. I'm going to do for the x direction because typically that's more important because we have our stresses or our bending stresses vertically, and we're concerned about bending moments. This is implying the bending moments on the ends of the beam, and typically Ix is of principal concern to us because we're going to have very high tensile stresses and very high compressive stresses, more so if we have large bending than if we have less bending. So in this case, we can say that Ix equals a summation, and there's there's 3 components. So we'll go from I equals 1 up to 3 of the moment of inertia of each of these components. So I'll write that as Ix, and I'll put like that. So it's a summation of the Ix values of each component, and there's the I. So that basically you do it for, you evaluate the moment of inertia for this one, the moment of inertia for number 2, moment of inertia for number 3, and you add them together. So what are the values that we're going to be using? We're essentially going to plug in this into here. We end up with a summation, again, I equals 1 to 3 for Ix prime plus a d squared evaluated for each of the components, so for 1, 2, and 3. So I'll put an I here. So this I would apply both to the moment of inertia value. In other words, different rectangles are going to have different moment of inertias. And it would also apply to the D value and the A value. They're all going to be unique to each of these components. And I'll walk through an example of how we evaluate this, because this can be a little confusing to get that right. All right, so I'm going to pause the video, then we're going to come back and we're going to look at an example of how we evaluate this moment of inertia for different kinds of composite areas. This is the cross-sectional area for which we want to evaluate our moment of inertia. It's, I don't know what you call it, maybe it doesn't have, but it has some kind of an angle bracket. So you can imagine this being the cross-sectional area of a very long beam basically coming out of the board. And it's 400 millimeters in this dimension. We have 400 millimeters for this piece here, 600 across, and the constant thickness of 100 millimeters. And what we're going to do is we're going to break it up into 3 pieces, and we're going to evaluate the moment of inertia for each of them. And as you might remember, when we add together those moment of inertias, we get the full moment of inertia for the entire cross-sectional area. All right, so how do we do that? There are probably multiple ways for which we could break this into pieces. We could break it into this piece, which would be 300 millimeters high. And there's this other one that's 600 across and 300 high here. In fact, that's what we're going to do. On the other hand, we could break it into 400 by 100. This piece would be 400 across, right? 600 minus 200 by 100, and then this one would be 400 by 100. But we're going to do it the first way, but you can do it either way. So I'll just draw in green our 3 areas. So I'll call this number 1, call this area number 2. This would be the entire area up to, yes, including here. Okay, that's our number 2, goes all the way across the full length, 600 across. And then we have our area number 3 over here. So these are 300 high by 100 across. This is the same, 300 high by 100 across. And what we're going to do is we're going to find the moment of inertia of each of these for a particular axis. And then we're going to add them together and get the moment of inertia for the entire area. All right, so the particular axis that we want to use, and this is almost always the case, is we want to evaluate the moment of inertia for the centroid through this area. And And we could evaluate the centroid, which you might remember is another double integral. And we actually had a methodology that we talked about for evaluating the centroid of composite areas, such as this, where you have like 3 pieces that make up a full area. However, if you look at it carefully and remember that the centroid is like a center of gravity, if we were to define an axis through this thing, we realize that the centroidal axis is going to go through, basically through the midpoint here. Okay, it's because half of our mass is below this, and half of our mass is above. So this is our x prime axis for which we're going to be evaluating our moment of inertia. And almost the trickiest part, the part that throws off many students, is how to evaluate this d value for each of our components that make up our composite area. And what it is, it's the distance between this axis and the centroid of each of the individual components. So for example, the centroid through this one, this is a rectangle, is essentially just halfway up. So it'd be like here, we'd have an axis here, this would be like our, what we've been calling x prime prime axis. Here's our y prime prime axis. So the d value for 1, in other words d sub 1, is going to be this distance here. I'll do it in one more color. All right, so how do we find that? We know this is 300 high, so it's 150 here. And this part here is 100 high, so that adds, we're only going to go halfway down, so that's another 50. So 150 plus 50, so the d value here is actually 200 millimeters. This d value, and I'm running out of room here, but I'll write it up here, 200 millimeters. And I'll, just for clarity, hopefully this is adding clarity, I'll put equals d sub 1. Okay, our d sub 2 value, in this case, the centroid of this centerpiece is the same, has the same center as the overall composite area. So d sub 2 is actually equal to 0. And I have nothing to point to, but I will write it here. So d2 equals 0. And the d3 value we're going to measure relative this point, but we have to define where our y prime prime or x prime prime axis is down here. And it'll go through this centroid, or the centroid of this number 3 rectangle. And it'll look something like this. And I'll put 3 primes, because to distinguish it from that axis. This is y prime prime prime. And the distance from here to here is, again, 50 plus 150 is 200. So that's our d3 value. We have a distance here of 200. d3 equals 200 millimeters. Okay? d2, that should be also millimeters. All right, so now we have everything we need, because we have our, well, we know how to calculate Ix prime with a hat on it. This should have a, if you didn't realize, it should have a hat implying it's through the centroid. Right, it's bh cubed over 12. We know the a values and we know the d values. One convenient way of doing this is to create a little table. Where am I going to do it? I'm going to, if you don't mind, I'm going to erase this because it's kind of in my way. And I'll show you the kind of table that I would expect that might help you in evaluating this. And it's going to kind of give you a guide to doing it in a way in which you're going to minimize the errors. Because it's easy to make errors on these when you're doing these, particularly like in a test or homework situation. So what we're going to do is, first thing we're going to have the basically the component number. That's COMP period component number. And it'll either be 1, 2, or 3. That's our 3 components. Component 1, 2, and 3. Next we'll put the D value here. And I'll put DI, and that'll be in millimeters. And that would be either what we have here, 200 for the first one. And we know it's 0 for the second one. And the third one is also going to be 200. And then we put here our B and our H values. And the B value of this one, this width is 100 millimeters. And the B value for the middle one is 600. And the B value, in other words, the width of this one is going to be 100. And it'll be 300 height, 100 height, and a 300 height. All right, now we're running out of room here, so I'm going to put in here, so we have D, this is also millimeters. Millimeters. All right, what else do we need? So now we're going to evaluate our IX values, because remember it's BH cubed over 12. So here we'll put IX prime, and this is going to be in units of, believe it or not, millimeters to the fourth. If you don't believe me, you see that you have an area which would have like squared length units times the square of a distance, so we end up with units of length to the fourth power. So those values, and I'm just gonna, these are essentially equal to BH cubed over 12. And I'll just write the values, I have them here. We ended up with 225 times 10 to the 6, 50 times 10 to the 6, and 225 times 10 to the 6. You'll notice that you have higher values for these than you do for the middle one. Why is that? Because these are farther away from the axis, from that centroidal axis. The farther away you get, the higher those values are going to be. They're also shaped so that they're more of the mass is further away because they're basically oriented like in a, what we call like a portrait mode, right? Up and down rather than across. All right, then we need to have our A. I'm actually gonna, since I'm running out of room, hold on a second. Okay, I was running out of room, so I've reoriented the camera. What I want to put in here are the A values, which are, A is just going to be our B times H values. Oops. Well, let me not put that there. Put that up here. B times H. And these are in millimeters squared. And these values are 3 times 10 to the fourth. You notice I'm putting these in scientific notation because the numbers are like quite large. They in fact have only like one significant figure that we have to actually represent. 3 times 10 to the fourth. Now the final thing we're going to put over here is the sum of these two values. So this is going to be Ix. This is the moment of inertia for each of our 3 components. And we're going to add them up at the bottom, and that'll give us our total moment of inertia. So this has units of m to the fourth power, millimeters to the fourth power, and this equals BH cubed over 12 plus AD squared. So I take this value, and then I add it to the product of this one squared times that one, and that'll give our value here. And the values are 1.425 times 10 to the 9th. Yep. 50 times 10 to the 6th. And again, 1.425 times 10 to the 9th. And if we add these all up, we end up with 2.9 times 10 to the 9th millimeters to the fourth. So that is our what we were looking for. This is the moment of inertia, Ix, about this axis through the centroid of our composite area. So this just gives you a framework for evaluating it in a way in which hopefully will minimize the number of errors that you might otherwise make if you were to evaluate the moment of inertia for each area singly using this method. All right, so I believe that's about all I wanted to cover today. If you have any questions, send me an email. Otherwise, I will see you next time in class.